Have you ever looked up at the night sky and wondered what secrets it holds? The universe is filled with objects so strange that our modern physics struggles to explain them. We're talking about cosmic monsters that can swallow entire stars like grains of sand, objects that bend space and time so powerfully that the familiar laws of nature simply break down. This isn't science fiction, it's a reality confirmed by science. Today we journey into the heart of one of the universe's greatest mysteries, black holes. For a long time, black holes were just a fascinating hypothesis, a wild idea on a blackboard. But in recent years, science has taken giant leaps forward. We now have undeniable proof that they exist. Thanks to incredible new telescopes, we can not only detect them, but also witness mind-boggling events like black hole collisions. Studying these enigmatic objects has become crucial for all of science. They push the limits of our knowledge and hold clues to understanding how stars are born, how galaxies evolve, and the very fabric of space and time. What happens to matter that falls into a black hole? Could they be gateways to other universes? We have so many more questions than answers, which makes the journey all the more exciting. So, what exactly is a black hole? Imagine a region in space and time where gravity is so intense that nothing, not even light, can escape. This is why they are called black holes. They don't emit or reflect any light, making them invisible. The idea stems from Einstein's groundbreaking theory of general relativity. He taught us that any object with mass warps the space-time around it. Think of the universe as a giant, stretched-out rubber sheet. If you place a bowling ball on it, the sheet dips and curves. The heavier the ball, the deeper the dip. A black hole is like taking that bowling ball and making it so incredibly heavy that it punches right through the sheet, creating an infinitely deep funnel. At the very bottom of this funnel lies something called a singularity. This is a point where all the mass of the black hole is crushed into an infinitely small space, creating infinite density. Here, our understanding of physics, all the equations that describe our world, become meaningless. They simply can't handle the concept of infinity. This is the ultimate frontier of science, a place where the rules as we know them no longer apply. Since we can't see a black hole directly, how do we know they're out there? Scientists are like cosmic detectives, looking for clues. When matter gets too close to a black hole, it gets caught in a cosmic whirlpool. This matter heats up to unimaginable temperatures, releasing a massive amount of energy in the form of X-rays. This creates a brilliant spinning ring around the black hole called an accretion disk. The intense glow of this disk is a dead giveaway, allowing us to pinpoint the location of the invisible object at its center. Another major clue is gravity. We can observe stars moving in very strange ways, orbiting what appears to be empty space. These bizarre orbital dances are convincing evidence that a massive invisible object, a black hole, is pulling the strings. Gravity also gives us another amazing tool, gravitational lensing. A black hole's immense gravity can bend the light from galaxies located far behind it. It acts like a giant cosmic magnifying glass, distorting and magnifying the images of these distant objects. It's a spectacular effect that confirms the presence of these gravitational titans. Two key concepts are crucial for understanding black holes: the event horizon and the gravitational radius. The gravitational radius, also known as the Schwarzschild radius, is the size to which you, d, have to compress an object for it to become a black hole. The more massive the object, the larger this radius. For example, to turn our Earth into a black hole, you'd need to crush its entire mass into a sphere just 2 centimeters across. For our Sun, you'd need to squeeze it down to the size of a small town, about 3 kilometers in radius. The surface of this sphere is the event horizon. This isn't a solid surface you can touch. It's a point of no return. It's a mathematically defined boundary in space. Once anything crosses it, whether it's a spaceship or a beam of light, it can never escape the black hole's pull. It's a one-way trip into the unknown. Any signal sent from beyond the event horizon can never reach us. Imagine for a moment if a black hole, even a small one, wandered into our solar system. Its gravity would be colossal. The delicate balance of our planet's orbits would be shattered. Earth could be flung onto a new chaotic path, or worse, ejected from the solar system entirely into the freezing darkness of deep space. The immense tidal forces would trigger catastrophic earthquakes and tsunamis, literally tearing our planet apart. The arrival of such an object would spell certain doom for our world. The story of black holes actually began long before Einstein, back in the 18th century. Scholars like Jean Michel and Pierre-Simon Laplace theorized about dark stars. Stars so massive that their gravity would be strong enough to trap their own light, rendering them invisible. However, at the time, light was thought of as a wave, so the idea didn't quite stick. Everything changed in 1915 with Einstein's theory of general relativity. He showed that gravity isn't a force, but a consequence of mass-curving space-time. His theory also revealed that time itself is not constant. The stronger the gravity, the slower time flows. This effect, called gravitational time dilation, is very real. We even have to account for it in our GPS satellites, which run slightly faster in orbit than clocks on Earth. Shortly after Einstein published his theory, a physicist named Karl Schwarzschild found the first exact solution to his equations, describing the gravitational field around a single massive object. His calculations included a strange region, the Schwarzschild radius, where physics seemed to break down. For decades, many scientists, including Einstein himself, were skeptical and thought these singularities were just mathematical quirks. But in the 1960s, the work of brilliant minds like Roger Penrose and Stephen Hawking proved that when a massive star dies, its collapse into a singularity is inevitable. Black holes were finally accepted as a real possibility. So how are these cosmic giants born? It all starts with the life and death of massive stars. A star begins as a vast cloud of gas and dust that collapses under its own gravity, forming a hot, dense core. Nuclear fusion ignites and a star is born. For millions or billions of years, the outward pressure from this fusion energy perfectly balances the inward pull of gravity. But this fuel won't last forever. The fate of a star depends on its mass. Stars much more massive than our Sun live fast and die young. When they exhaust their fuel, the delicate balance is broken. Gravity wins. The core collapses catastrophically in a fraction of a second, triggering a spectacular explosion known as a supernova. This explosion can outshine an entire galaxy for a brief time. What's left behind is the crushed remnant of the core. If it's massive enough, nothing can stop its collapse, and it continues to shrink until it becomes a black hole, a new enigma born from the ashes of a star. Studying black holes is more than just an academic exercise. It's a quest to understand the fundamental laws of our universe. Thank you for joining me on this journey into the cosmic unknown. If you enjoyed this video, please give it a thumbs up, and don't forget to subscribe and hit that notification bell for more adventures into the wonders of science. See you next time.